So hi everybody, my name is, as you said, Bouchard from the University of Ottawa, and today I'm going to talk on alternative in-gas SIGs, high-efficiency multi-junction solar cell design. So I'll start with a quick motivation, some basic solar cell physics. I'm going to talk about the simulation environment, then SIG solar cell, multi-junction solar cell, what are the challenges in our simulation, and then some simulation results in conclusion. So photovoltaics are gaining a lot of interest in the past few years because of the fact that they are renewable energy. And at this time, multi-junction solar cell are the state-of-the-art photovoltaic device demonstrating the highest efficiencies. And at this time, standard multi-junction solar cells are composed of in-gas, and germanium. But as we will see, germanium presents some disadvantages. So we are interested in exploring alternative material that could replace germanium in a triple junction solar cell. And as we will see, copper, indium, gallium disulfide, which I will just call SIGs, could be a good alternative in terms of cost. So solar cells are made of semiconductor, which has a valence band and conduction band separated by an energy gap that we'll just call the band gap. And when we have an incident photon of energy higher than the band gap, it will be absorbed by the electron in the valence band and be promoted to the conduction band, creating an electron-hole pair. And in the conduction band, the electron could contribute to the current, or it can recombine with this hole through different recombination processes. There's the radiative recombination, which is when the electron in the conduction band just spontaneously emits a photon, or the electron will cool down to the valence band through mid-gas states. So we can characterize our solar cell with its JV curve, so that's the JV curve, and its JV metric. So we have the JSC, which is a short circuit current, the VOC, which is the open circuit voltage. Here we have the power curve, which is just the current times the voltage, and we have a maximum power point there, which is there on the JV curve. And from there we can define the fill factor, which is just the maximum power point on JSC VOC, which is just an indicator of the squareness of our JV curve. And we also have the efficiency, which is just the ratio of the maximum power point on the incident light power. So the efficiency, that's what we want to be maximum. We can also define the EQ, which is the external quantum efficiency, which is the probability that an incident photon of energy E will deliver one electron-hole pair to the external circuit. So here we have an EQ curve of a single junction solar cell, and in the background I've put a photon flux curve. So our solar cell will only absorb this range of wavelengths. So as you can see, we have a lot of photons that are not absorbed, which means a lot of energy losses. I'm going to talk quickly about the simulation environment. So we are using TCAD Centaurus, which is a program that solves the said nonlinear semiconductor device equation, consisting of Poisson's equation, continuity equation, and drift diffusion equation to simulate the current voltage characteristic to the device. So they're here. The outputs that we have from this simulation device is the JV curve, EQ curve, and much more, such as energy band diagram and combination mechanism, electric field current concentration. The inputs that we get to the simulation device is by specifying each layer of our device by specifying the thickness, the doping level, and the material properties. And we can add an anti-reflection coating on our device.